Far beyond the planets, two small spacecraft drift quietly into the dark, still whispering back to Earth. They were built in the 1970s, launched within weeks of each other, and sent on a journey no human-made object had ever attempted. Tonight, as you settle into stillness, consider where they are now, drifting through a region so distant that sunlight takes more than 20 hours to reach them. Their plutonium hearts grow fainter each year, their signals weaker, and yet somehow they continue. Voyager 1 and Voyager 2, the farthest travelers our species has ever made. Welcome to Let's Learn While You Sleep. Tonight, we drift outward, far past the warm embrace of the sun, far past the orbits of the gas giants, to follow the quiet trajectory of two of humanity's most remarkable creations. The Voyager probes were launched in the summer of 1977, designed at first only to survey the outer planets, and yet they have continued onward for nearly half a century, sailing into the strange and uncharted boundary where our solar system begins to dissolve into the great galactic ocean beyond. As you rest, let your thoughts travel with them, gently, slowly, across billions of kilometers of empty space. We will explore how they were built, what they discovered, where they are now, and what it truly means to leave the solar system. There is no need to remember anything tonight. Let the words become a soft current, carrying you outward into the calm and luminous dark. In the early 1970s, scientists at NASA's Jet Propulsion Laboratory recognized that a rare alignment of the outer planets was approaching, an arrangement that occurs only once every 176 years. Jupiter, Saturn, Uranus, and Neptune would gather along a graceful curve, allowing a single spacecraft to use the gravity of each world to slingshot toward the next. It was a celestial opportunity too elegant to ignore. From this realization, the Voyager mission was born. Two identical probes were designed, each weighing roughly 722 kilograms, each carrying 11 scientific instruments, and each powered not by sunlight, which would grow too faint in the outer reaches, but by the slow radioactive decay of plutonium-238. These small generators produced warmth and electricity quietly, year after year, like a steady heartbeat in the cold. The engineers who built them could not have known with certainty how long the probes would survive, but they prepared for everything they could imagine: redundant systems, hardened electronics, careful shielding against radiation. Voyager 2 launched first on August 20th, 1977, despite its name. Voyager 1 followed 16 days later on September 5th, on a faster trajectory that would let it overtake its twin. Both rose from Cape Canaveral on Titan III Centaur rockets, lifting away from the Florida coast into a sky that had no idea what was being entrusted to it. Within weeks, they were beyond the moon. Within months, beyond Mars. And yet, in those early days, no one truly spoke of interstellar space, because the mission's first goal was simply to reach Jupiter and survive long enough to send back pictures. Everything beyond that was a gift, a possibility, an open question. The probes carried with them not only instruments, but also small golden phonograph records, encoded with sounds and images of Earth, in case, somewhere in the long darkness ahead, something or someone might one day find them. It was an act of profound optimism, a message in a bottle, cast into the cosmic sea. The golden records carried aboard each probe are perhaps the most poetic artifacts ever made by human hands. They are gold-plated copper phonograph discs, 12 inches in diameter, designed to last, in principle, for at least 1 billion years in the vacuum of space. Each disc was curated by a committee led by the astronomer Carl Sagan, and each contains a remarkable selection of sounds chosen to represent our world. There are greetings spoken in 55 languages, from ancient Akkadian to modern Mandarin. There are the sounds of wind and rain, of crashing waves, of crickets and frogs and whale songs. There is the laughter of a child, the kiss of a mother, the beating of a human heart. And there is music, drawn from every corner of the earth. A Bach prelude, a Navajo night chant, Senegalese percussion, a Peruvian wedding song, and Chuck Berry's Johnny B. Good, chosen to represent the energy of human rock and roll. The records also contain 115 analog encoded images, instructions for playback inscribed in symbolic diagrams on the cover, and a small sample of uranium-238, whose slow radioactive decay would serve as a clock by which any future finder might calculate when the spacecraft had been launched. Whether anyone or anything will ever find them is, of course, profoundly uncertain. The distances between stars are so vast, and the universe so largely empty, that the probes may drift for billions of years without encountering another world. And yet the gesture remains. Tonight, somewhere in the dark, those golden discs are still there, sealed in their aluminum covers, untouched by erosion, untouched by time as we experience it on Earth. They carry the patient sound of a single human heart, beating steadily, recorded long ago, still traveling outward at over 60,000 kilometers per hour. A whisper of who we were, who we are, drifting endlessly through the silence between the stars. Voyager 1 reached Jupiter in March of 1979, sweeping past the giant planet at a distance of roughly 349,000 kilometers from its cloud tops. What it sent back astonished the world. The Great Red Spot, a storm larger than Earth itself, was revealed in unprecedented detail, swirling with currents and eddies that had been raging for centuries. The probe also discovered a thin ring around Jupiter, a feature that had previously gone unnoticed, and it captured the first close images of the planet's volcanic moon, Io. There, the Voyager imaging team saw something no one had expected: plumes of sulfurous material erupting hundreds of kilometers into space, evidence that Io was the most volcanically active body in the solar system. The discovery was so unexpected that engineer Linda Morabito, who first noticed an anomalous crescent in one of the images, initially thought it might be a flaw in the data. Then came Saturn. Voyager 1 arrived in November 1980, capturing breathtaking views of the planet's rings, revealing their intricate structure, their countless braided strands, their tiny shepherd moons keeping order along narrow gaps. The probe flew close to Titan, Saturn's largest moon, which was found to possess a dense, hazy atmosphere of nitrogen and methane, a world hidden beneath its own veil of orange clouds. This Titan encounter, however, came at a cost. The trajectory required to study the moon bent Voyager 1's path upward, out of the planetary plane, ending any chance of visiting Uranus or Neptune. Voyager 2, traveling more slowly, took the longer path. It reached Uranus in January 1986 and Neptune in August 1989, becoming the only spacecraft ever to visit those distant, frozen worlds. At Neptune, it captured the Great Dark Spot, a vast atmospheric storm, and discovered geysers of nitrogen erupting from the icy surface of the moon Triton. With each encounter, the probes redefined what we knew. With each encounter, the solar system grew stranger, richer, and more alive. After Neptune, Voyager 2 followed its sister out of the planetary plane, both probes now climbing into regions of space that had never before been measured directly. The Sun, even at this distance, continued to exert its quiet influence, not through gravity alone, but through a constant outpouring of charged particles known as the solar wind. This wind, streaming outward at speeds of hundreds of kilometers per second, carves an enormous bubble in the surrounding interstellar medium, a bubble called the heliosphere. Within the heliosphere, the Sun's magnetic field dominates. Beyond it lies true interstellar space, where the magnetic fields and particles come from other stars, from ancient supernovae, from the slow drift of the galaxy itself. For decades, scientists wondered where exactly this boundary lay and what it would feel like to cross it. The Voyagers were carrying the only instruments capable of finding out. In February 1990, at the request of Carl Sagan, Voyager 1 turned its cameras one final time, looking back across the solar system to capture a series of images that would become known as the family portrait. In one of these frames, Earth appeared as a tiny point of light, less than a single pixel across, suspended in a beam of scattered sunlight. Sagan would later call it the pale blue dot, and write that on this distant speck, every person who had ever lived had lived out their lives. Every joy, every war, every quiet evening by a fire. After this final photograph, Voyager 1's cameras were powered down forever to conserve energy for the long journey ahead. From that moment on, the probes would no longer see. They would only feel. They would measure magnetic fields, count charged particles, listen for plasma waves. They would become, in effect, blind explorers reading the texture of space with their fingertips, drifting onward into a darkness from which no image would ever return. The early 2000s, both Voyagers had crossed the orbit of Pluto, sailing into a region scientists call the heliosheath, the outer layer of our sun's vast magnetic bubble. This bubble, known as the heliosphere, is shaped by the solar wind, a steady stream of charged particles flowing outward from the sun at roughly 400 kilometers per second. For most of human history, we had no way of knowing where this bubble ended, or whether it ended at all. The Voyagers, drifting silently through unmapped territory, became the first instruments to sense its edge from within. In December of 2004, Voyager 1 crossed what mission scientists named the termination shock, a turbulent boundary where the solar wind slows abruptly as it begins to collide with the thin gas of interstellar space. Voyager 2 followed in August of 2007, taking a slightly different path and offering a different perspective on this strange frontier. The data they returned was unexpected, even to the engineers who had designed them. The shock was not a smooth boundary, but a region of swirling magnetic fields, plasma waves, and pressure fluctuations, more like a shoreline beaten by ocean waves than a clean line drawn in space. And yet, even crossing this shock, the probes were not truly free of the sun. The heliosheath extended much farther than anyone had predicted, a vast and quiet region where solar particles slowed, swirled, and mingled with whispers from the stars beyond. Consider for a moment what this meant for human understanding. We had launched 2 small craft, weighing less than a compact car each, and they had become our first emissaries to a place we had only theorized about. They were sending back measurements of magnetic fields and particle counts from distances so great that radio signals, traveling at the speed of light, took more than 14 hours simply to reach Earth. Somewhere in that darkness, our machines were still listening, still patient, still loyal to the mission written into them decades earlier by hands and minds that had long since aged, retired, or passed on. Then, on a quiet day in August of 2012, something extraordinary happened. Voyager 1, drifting at a distance of roughly 121 astronomical units from the Sun, crossed a threshold that no human-made object had ever crossed before. The density of charged particles around it shifted suddenly. The magnetic field changed character. The Sun's familiar wind, which had cradled the probe for 35 years, faded away, replaced by the slow, cold pressure of the interstellar medium. Voyager 1 had entered interstellar space. It is worth pausing on what those words actually mean. For the first time since life emerged on Earth, an object built by human hands had left the protective bubble of our Sun and entered the space between the stars. The announcement, made by NASA in September of 2013, after careful analysis of the data, marked a quiet but profound moment in the history of our species. We had become, in the smallest possible way, an interstellar civilization. Voyager 2 followed its sibling across this boundary in November of 2018, confirming with its own independent measurements what Voyager 1 had reported. The 2 crossings, separated by 6 years and millions of kilometers, revealed that the heliopause, the true edge of the Sun's influence, is not a static wall, but a shifting, breathing surface, expanding and contracting with the rhythms of the solar cycle. And yet, even now, even having crossed this remarkable frontier, the Voyagers are not truly leaving the solar system. The Oort cloud, a vast spherical shell of icy bodies thought to surround our Sun at distances of up to 100,000 astronomical units, still lies ahead. Scientists believe it will take Voyager 1 roughly 300 years simply to reach its inner edge, and perhaps 30,000 years to pass through it entirely. The probes are interstellar travelers, yes, but they are also still, in a sense, falling slowly away from the Sun that built them, like leaves drifting away from a fire on a still autumn evening, carrying with them the warmth of where they came from. The instruments that allow the Voyagers to keep speaking to us are powered by something quietly remarkable, a device called a radioisotope thermoelectric generator, or RTG. Inside each probe sits a small reservoir of plutonium-238, a radioactive isotope that decays slowly, releasing heat in the process. That heat is converted directly into electricity through thermocouples, with no moving parts to wear out, no fuel to refill. When the Voyagers launched in 1977, each RTG produced roughly 470 watts of electrical power, enough to run their instruments, transmitters, and computers with energy to spare. But plutonium-238 has a half-life of about 87 years, meaning that with each passing decade, the available power slowly fades. Today, more than 4 decades into the mission, each Voyager produces only about 250 watts, and that number drops by roughly 4 watts every year. To keep the probes alive and transmitting, engineers at NASA's Jet Propulsion Laboratory have been carefully shutting down systems one by one. Cameras were powered off long ago, since there was nothing left to photograph in the darkness. Heaters that kept certain instruments warm have been turned off, allowing those instruments to operate at temperatures far below what they were originally designed to endure. And remarkably, many of them continue to function, stubbornly returning data from a place no other machine has ever been. Consider the engineering required for this slow, graceful aging. Every command sent to the Voyagers must travel for more than 20 hours, one way at the speed of light. Every response takes another 20 hours to return. There is no quick fix, no live debugging, no emergency override. When something goes wrong, the team on Earth must diagnose it through fragments of data, often working with software written in the 1970s in computer languages that few engineers today still understand. And yet, decade after decade, this small dedicated team has kept the probes alive, nursing them through power losses, memory failures, and the slow, inevitable cooling of their distant, fading hearts. Current estimates suggest that the Voyagers will continue to transmit usable scientific data until sometime in the mid-2030s, perhaps a little longer if engineers can find more creative ways to conserve power. After that, one by one, the remaining instruments will fall silent. The transmitters will weaken, the signals will fade beneath the cosmic background noise, and the conversation between Earth and her 2 oldest interstellar children will quietly come to an end. But the probes themselves will not stop. They will keep traveling, carried forward by the momentum imparted to them nearly half a century ago, drifting through the dark at roughly 17 kilometers per second relative to the Sun, generation after generation, in absolute silence. In about 40,000 years, Voyager 1 is expected to pass within roughly 1.5 light-years of a small dim star called Gliese 445 in the constellation Camelopardalis. Voyager 2, on a different trajectory, will drift past another modest star, Ross 248, around the same time. Neither probe will enter another solar system in any meaningful sense, but they will, for brief astronomical moments, become the closest human artifacts to other suns, and then they will keep going. The golden records, sealed against the slow erosion of cosmic radiation and micrometeoroid impacts, are expected to remain readable for hundreds of millions, perhaps even billions of years. Long after the last human voice on Earth has been silenced, long after our continents have rearranged themselves, long after our sun has begun its own slow death, those small, gleaming disks may still drift through the galaxy, carrying the laughter of children, the songs of whales, the greetings of 55 languages, and the quiet image of a hand reaching out in friendship. They are, in a very real sense, the most enduring monuments our species has ever built. And somewhere in that immense darkness, somewhere between one star and the next, they continue their journey, faithful, silent, patient, carrying us with them into a future we will never see. Consider for a moment what each Voyager carries with it into that endless night. Bolted to the side of each spacecraft is a gold-plated copper phonograph record, 12 inches across, sealed within an aluminum cover, etched with quiet instructions. These are the golden records, conceived under the guidance of the astronomer Carl Sagan and a small committee of scientists, artists, and writers who were given less than a year to decide what humanity might say to the universe. They chose in the end not a single message, but a chorus. Greetings spoken in 55 languages, from ancient Akkadian to modern Mandarin, drift across the grooves alongside the sound of a kiss, the cry of a newborn, the song of humpback whales, and the soft footfalls of a person walking through grass. There is music too, Bach and Beethoven, Chuck Berry, a Navajo night chant, Bulgarian shepherdess songs, a Peruvian wedding tune, the haunting tones of a Javanese gamelan. The record holds 115 images, encoded as audio waveforms, picturing the structure of DNA, the dimensions of the human form, the geometry of mountains and rivers and cities. And there is silence too, long stretches of it, woven between the sounds, as if to acknowledge that any message sent across such distances must be patient. The records were not designed to be found. The probability of any intelligence ever encountering them is, by any honest reckoning, vanishingly small. Yet the gesture itself was the point. To craft something beautiful and place it into the void, knowing it may drift untouched for 1 billion years, is a profoundly human act. The records are coated in a layer of uranium-238, a slow-decaying isotope that future finders could use, in principle, to determine when the message was sent. Even our timekeeping, in this gesture, was made to last across geological scales. And so the Voyagers carry forward not just instruments and circuitry, but a quiet whisper of who we were and what we wished to say. Now imagine, if you will, the journey ahead. The Voyagers are moving at roughly 17 kilometers per second relative to the Sun, a speed that, on human scales, seems almost unimaginable, yet, on the scale of the galaxy, is a slow and patient drift. At their current pace, Voyager 1 will not approach another star for tens of thousands of years. In roughly 40,000 years, it will pass within about 1.6 light-years of a small, dim red dwarf called Gliese 445 in the constellation Camelopardalis. That star will by then have drifted closer to our Sun, and the meeting, if such a word can apply to objects separated by trillions of kilometers, will be the closest stellar encounter of Voyager 1's known trajectory. Voyager 2, traveling a different path, will pass within about 1.7 light-years of the star Ross 248 in roughly the same span of time. Neither encounter will involve any gravitational capture, any dramatic event, any moment of contact. The probes will simply continue on, their courses adjusted only by the faint pull of distant masses, their solitude unbroken. And after these encounters, the journey only deepens. The Voyagers will continue outward into the disk of the Milky Way, drifting among the stars of the Orion Arm, slowly circling the galactic center along with the Sun itself. Once every 225 million years or so, they will outlast the Earth. They will outlast, in all likelihood, the Sun's stable burning. When our star eventually swells into a red giant, some 5 billion years from now, and the inner planets are consumed or scorched into lifeless husks, the Voyagers will still be out there, still drifting, their gold records still intact, still carrying the soft echo of a Bach prelude and the laughter of a child. They will become, in a very real sense, our longest-lasting artifacts, older than any monument, any pyramid, any city of stone. They are messages in bottles cast upon an ocean of time so vast that the word ocean barely applies. Yet, even as we contemplate these immense distances, there is something tender in remembering how the Voyagers were built. They were not crafted by some distant, faceless future. They were shaped by human hands in clean rooms in Pasadena, California, in the mid-1970s, by engineers and technicians who soldered circuits, polished mirrors, and tested instruments under fluorescent lights. The onboard computers carry only about 69 kilobytes of memory each, a quantity so small by modern standards that a single photograph from a contemporary phone would not fit within it. And yet these modest machines have navigated the outer solar system, executed thousands of commands, weathered cosmic radiation, and continued to function for nearly half a century. The engineering teams who designed them are now mostly retired, some have passed away, and a small dedicated group at NASA's Jet Propulsion Laboratory continues to communicate with the spacecraft using software languages that are, in many cases, no longer taught. They maintain old manuals, hand-annotated schematics, and a deep institutional memory passed down across generations of mission specialists. To send a command to Voyager 1 today is to speak in a language that is itself a kind of fossil. Assembly code, written in an era before personal computers were common in homes. And the response, when it returns, arrives more than 43 hours later, faint and patient, decoded by antennas the size of buildings. There is a quiet poetry in this, a conversation conducted across decades in a tongue half forgotten, between aging machines and the aging humans who still remember how to listen. Every command sent must be considered carefully, for there is no margin for error, no chance to recover from a mistake at such distance. And so each transmission becomes a small ceremony, a measured, deliberate act of care across the void. The Voyagers, in this way, are not only spacecraft, they are an unbroken thread, a relationship maintained across half a century, a quiet act of devotion between a small group of people on Earth and two distant travelers carrying our gift outward. Somewhere in that darkness, billions of kilometers away, Voyager 1 is doing something it has done for 46 years. It is turning, slowly, almost imperceptibly, to keep its high-gain antenna pointed back toward a small blue world it left behind long ago. Its star tracker locks onto a single distant star. For decades, it used the bright star Canopus as a reference, and from this anchor, it orients itself in the vastness, knowing where home lies by the geometry of starlight. It is a gesture both mechanical and deeply moving. A small machine, alone in the dark, holding its face toward us across an unimaginable gulf, so that whatever signal it sends might find its way back. And we, on this side of the silence, listen. The Deep Space Network, 3 great radio facilities spaced roughly evenly around the Earth, in California, in Spain, and in Australia, ensures that at any hour of the day, somewhere on our rotating planet, an antenna is turned outward, gathering the faint whispers of the Voyagers and the other distant probes. The signal that reaches us from Voyager 1 has a power, by the time it arrives, of less than a billionth of a watt. It is detected only because we have learned, over decades, how to listen for whispers in a sky full of noise. Consider what that means. Across the void, 2 small, fragile, human-made objects continue to speak. They tell us what they sense, the strength of the galactic magnetic field, the density of cosmic rays, the soft pressure of plasma flowing between the stars. They send back numbers, patiently, faithfully, hour after hour. And in those numbers, gathered and stored and studied, we are learning the texture of the space between stars, a region that until the Voyagers crossed into it, no instrument had ever directly measured. They are our first true emissaries to the interstellar medium, the first objects in human history to taste the wind that blows between the suns. Consider for a moment the engineering miracle that makes this continued whisper possible. The Voyagers are powered not by sunlight, which at their distance is far too faint to be useful, but by radioisotope thermoelectric generators, devices that convert the heat released by decaying plutonium-238 into modest amounts of electricity. When the probes launched in 1977, these generators produced roughly 470 watts each, about the energy required to illuminate a few household bulbs. But plutonium, like all radioactive material, decays steadily with time, and the generators have been losing approximately 4 watts of output each year. Today, both spacecraft operate on a sliver of their original power, and engineers at NASA have spent decades carefully turning off instruments, heaters, and subsystems, one by one, to extend the missions as long as possible. It is a slow, deliberate act of conservation, like dimming the lights in an old house room by room so that one small lamp may keep burning a little longer. And yet, despite the cold, despite the loss of power, despite the staggering remoteness, several instruments still function. The plasma wave subsystem, the magnetometer, the cosmic ray detector, these elders of interstellar exploration still listen, still measure, still report. There is something humbling in this. The radio signal that leaves Voyager 1 is incredibly faint by the time it reaches Earth, on the order of a tenth of a billionth of a watt, weaker by far than the signals from distant quasars. To capture it, NASA uses the vast dish antennas of the Deep Space Network, scattered across California, Spain, and Australia, each a precise listening cup tilted toward the stars. The signal takes more than 22 hours to travel back, crawling at the speed of light across the void, arriving softly, patiently, like the last echo of a song played long ago. And when the engineers finally read those numbers, those tiny variations in plasma density and magnetic field strength, they are reading messages from a place no human has ever been, written by a machine that has not stopped working in nearly half a century. Carried aboard each of these fading machines is something more than instruments, more than circuitry, more than the cold logic of science. Bolted to the side of each spacecraft is a golden phonograph record, 12 inches across, plated in gold to resist the slow corrosion of cosmic radiation. These are the golden records, conceived by a committee chaired by the astronomer Carl Sagan, and they carry, in their grooves, a portrait of Earth as it existed in the late 1970s. There are sounds: the crash of surf, the call of a humpback whale, the patter of rain, the laughter of a child, the rhythm of a human heartbeat. There are greetings spoken in 55 languages, from ancient Akkadian to modern Mandarin, each voice offering some small phrase of welcome to a listener no one expected ever to exist. There is music, carefully chosen across cultures and centuries: a Bach prelude, a Navajo night chant, a Peruvian wedding song, Chuck Berry playing Johnny B. Good, the gentle plucking of a Japanese shakuhachi flute. And there are images, encoded as analog waveforms, showing mathematical principles, the structure of DNA, anatomical drawings, photographs of mountains and oceans and snow, and the silhouettes of human beings holding hands. The records were never really meant for aliens, not in any practical sense. The probability of another civilization finding them is vanishingly small, and the timescales involved are almost beyond comprehension. They are meant, in a deeper way, for us. They are a message in a bottle thrown into the cosmic ocean, a quiet declaration that here, on a small blue world orbiting an unremarkable star, there once lived a species that looked up at the night sky and wondered whether it was alone. And long after our cities have crumbled, long after our continents have rearranged themselves, long after the sun itself has swollen into a red giant and consumed the inner planets, those gold-plated records will still drift through the dark, carrying the sound of whale song and a child's laughter, preserved in silence among the stars. And so for tonight, we leave the Voyagers where they are, drifting steadily outward, each one carrying its golden record, its faint radio voice, its quiet plutonium warmth. Voyager 1 is now more than 24 billion kilometers from Earth, and Voyager 2 follows behind, both still sending back whispers that take many hours to reach us. They will continue, long after their instruments fall silent, long after the last signal fades, traveling for tens of thousands of years before passing near another star. There is something deeply peaceful in that thought, that somewhere, right now, two small machines built by careful hands are sailing through the great dark, faithful and patient, never tired, never afraid. Let that image settle softly in your mind as you rest. The vastness is not empty. It is full of motion, full of meaning, full of small bright travelers carrying pieces of who we are into the silence beyond. Breathe slowly, drift gently. The journey continues, and you are safe here. If your mind found rest among the stars tonight, you are always welcome to return. There are countless more journeys waiting, more quiet wonders to drift through together. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.